The ratio test gives us a simple limit formula that we can plug into, and one will compute the limit and it will immediately tell us whether a series converges or diverges. So let's dig into a little bit this concept, and this is the case that shows that a series converges. So what does that actually mean here? Well, what it's saying is that we could kind of take this an plus 1 over an is less than 1, so then I can move this an to the other side. And so the idea behind it is that future terms are always smaller than previous terms. So basically what this is saying, because this is less than 1, not only are all the future terms getting smaller than the previous terms, but they're getting smaller at a ratio less than 1 as n goes to infinity. And so that's why things are getting smaller. And in fact, what that's saying is that when you add all these up, they're getting smaller and smaller and smaller. And eventually they get so small that the sum is finite, because the future terms get so much smaller than the previous terms. So that's the idea behind all that. And then it turns out that all you have to do is just reverse that inequality here. And if it's greater than 1, then immediately we know that the series diverges. And that's easy to see because the future terms are getting bigger than the previous terms. The top here is larger than the bottom because the fraction is greater than 1. So that means that the things we're adding up are getting larger and larger, and you could see using the series divergence test why this series would have to diverge. So let's take a look at an example where we use this. So we're going to show that this series converges using the ratio test, and then we're going to give its value. Okay, so first things first, we'll show that the series converges using the ratio test as we were asked. So how do I use the ratio test? Well, I have this limit that I just plug into. The limit as n goes to infinity, take the absolute value, and we throw that in there because this allows us to handle negative sequence terms as well. And so we're just going to take this future term over the previous term. So what does that mean for us? Well, basically, whatever your series is adding up, that sequence term in the series, we're going to put that on the bottom. And then on the top, what are we going to do? Well, we have an, but it's plus 1. So every time I have an n in my formula, I add a 1 to it. And I can see that I forgot the 4n on the bottom here. So on the top, I won't forget it, but it should be a plus 1. And at this point, I notice that, well, in this particular series, everything is positive, so I'll just scratch out those absolute value signs. And to make my life a little bit easier, I'm going to rewrite this fraction of fractions into the top fraction times the reciprocal of the bottom fraction. Okay, so let's compute this. First things first, I can split up the bottom here. This is the same thing as 4n times 4 to the 1 power, and I can cancel the 4n's and then pull out that 4 to the 1, which is a 4 on the bottom. And then what does that leave me with? So I pulled out this. I'm left with 3n plus 1 all over 3n plus 1. Alrighty. What can I do here? Well, I think I should factor out 3 to the n out of everything. If it was e to the n, I might use L'Hopital's rule. But with 3 to the n, I think it's going to be easier if I just go ahead and just factor out 3 to the n. So what's left on the top? Well, here I had an extra 3 plus 1 over 3 to the n. On the bottom I have 1 plus, and then here I have 1 over 3 to the n. So those cancel with each other. And now I'm going to take this limit as n goes to infinity, and I get this goes to 0 and that goes to 0 because it's 1 over infinity form. So I'm left with 3 over 1. So 1/4 times 3 over 1, that's 3/4. So now at the end of the day, I've figured out the value of this limit, and the ratio test says if that limit is less than 1, and it sure is, 3/4 is less than 1, therefore the series converges. If it was greater than 1, I would have said diverges, but it's less than 1, so I say the series converges, and I would be done with the problem, except that this problem is special because I'm asked to find its value. And I usually can't do this, and I definitely cannot find its value using the ratio test. But in this particular problem, there must be some other way I can find its value. And it turns out it's almost a separate problem. I can take the series, 3 to the n plus 1 over 4 to the n, and where does it begin with? It begins with n equals 0 to infinity. And I could split this up into two different series. I've got n equals 0 to infinity, 3n over 4n, plus 1 over 4 of the n equals 0 to infinity. And both of these, now that I've split it up, I have two different geometric series. In this case, I have 3/4 to the n with a 1. And it's important that it starts at 0 here. Here I have 1 times 1/4 to the n. And I'll use the geometric series form, noting that 3/4 absolute value is less than 1, and 1/4 absolute value is less than 1. So both of these I can use the geometric series formula to get a over 1 minus r. Here I have a over 1 minus r. Remember that this would be my a, that would be my r, this would be my a in this problem, and that would be my r in this problem. So what I end up with is 1 over 1/4 plus 1 over 3/4. 4 plus 4/3, that gets us, what does that add up to? That'd be 16/3. And that's the value of the series. All right, something to keep straight, because it's easy to forget, is that a lot of people will think that 3/4 is the value of the series. That is incorrect. 3/4 is simply what we get by taking the ratio test. It's just some number from some made-up limit that allowed us to show that because we got a ratio of less than 1, terms are getting smaller at a rate of about 3/4. So they're getting 3/4 smaller each time. That means that they're getting small enough, fast enough that the series will end up converging. But we'll have to use alternate techniques to show that we get a convergent sequence. Not only that it converges, but it converges to a specific value of 16/3. And if you want to convince yourself of this, well, just come up here to this infinite sum. What am I actually adding up? I'm adding 3 to the 0 plus 1 over 4 to the 0 plus 3 plus 1 over 4 plus 9 plus 1 over 16. So what do I have? I have 2 plus 1 plus 10/16. So already I have here 10/16 is, plugging that into a calculator, I have 3.625 for just the first 3 terms. If I add those up, 16/3 is 5.33. So obviously I haven't added up enough terms here to get this close enough. I've only added 3 things here. Here I've added infinitely many things, 3 repeating, of course. But you can kind of see how if I kept adding terms here, I would eventually get a number close to, but not quite, 5.33 repeating. Okay, that's enough of that example. Let's move on to a different one. The ratio test really shines when you're dealing with factorials. because it's very well suited for canceling factorial terms. So let's take a look at how I would approach this problem. Notice that it does not ask me what the value of the series is, because I can't figure it out using the ratio test. I can only figure out whether it converges or diverges. So the ratio test says I'm going to take the limit as k goes to infinity of an plus 1 divided by an. K goes to infinity. I'm sorry, we're using k's instead of n's in this problem. All right. All that really matters is that I rewrite the sequence on the bottom, the kth term, and then on the top I do the same thing, but I add 1 to all my k's. And use parentheses liberally when you're doing this. Every time you see a k, replace it with k plus 1 in parentheses. All right. Now I'm making a big show of drawing these absolute value signs, but now I'm realizing, well, heck, everything is positive. I can get rid of my absolute value signs. I only have to worry about those if there's negatives involved. Next, I'm going to rewrite the top fraction. So I'll write that as 2k plus 2 factorial on the top, divided by 3 times k plus 1 factorial on the bottom. Oh, nope, be careful, there's a square there. I forgot to rewrite the square from the original problem. So all that is going to be squared. Times, now I'm going to flip the bottom. 3k factorial gets squared, divided by 2k factorial. Okay, so again, I mentioned the ratio test really shines with factorials. It's the best way to handle a series involving factorials. Here on the top, I see that I have 2k plus 2 factorial. What does that mean? It means I'm taking all the numbers from 1 up to 2k plus 2 and multiplying them together. That's the same thing as taking all the numbers from 1 to 2k multiplied together. That's 2k factorial. But I still need the next two terms, 2k plus 1 and 2k plus 2. All right. On the top here, on the right, I have still 3k plus 1. In fact, instead of writing that as a square, let's just write it as 2k factorials multiplied together. Easy enough. Here on the bottom left, I still have that 3. And k plus 1 is all the numbers through k plus 1 factorial is all the numbers through k multiplied together times k plus 1. But there's two of them, so I'll write another k factorial and another k plus 1. So now that we're here, a lot of stuff should cancel pretty nicely. My 2k factorials cancel. My k factorials cancel here, here, and here. And so it's a big old mess, but what does that mess end up being? Well, I can take, I see that there's a couple of 3's. I can cancel those as well, huh? So I'll cancel this 3. I cancel that 3. And so what I end up seeing here is limit as k goes to infinity. I can split this up into two separate things. I got 2k plus 1 over a k plus 1. And then I also have a 2k plus 2 over another k plus 1. You could combine these or do them separately. It doesn't really matter. Both of these limit to 2. 2 times 2 is 4. So at the end of the day, what's going on here? Well, 4 is bigger than 1. Okay, and if it's bigger than 1, we can then conclude that the series diverges. And it diverges because future terms get about 4 times bigger than previous terms. Every time you go through the sequence that we're adding up, these sequences are getting about 4 times bigger each time from term to term. There's no way that's going to add up to something finite. The series will diverge in this situation. And that's probably another reason why it didn't ask us to find its value, because there is no value. It doesn't converge, so therefore it has no finite value when you add up the infinite sum. Okay, well, last up, I want to point out this little note here. Another test must be used if the limit you get is 1. Remember that in the statement of the ratio test, I said that it converges if it's less than 1, and it diverges if it's greater than 1. But if the limit is equal to 1, then things may or may not be getting smaller, but they aren't getting smaller fast enough to tell whether it converges or diverges. Okay, and so this example is a great way to show that you can have a divergent series and the limit's 1, but you could also have a convergent series and the limit is 1. So let's take a look at this. So there's two parts. The first part is we're going to show that the divergent series, remember that n equals 1 to infinity, 1 over n, 1 plus 1 half plus 1 third plus 1 fourth, that diverges. It's a harmonic series. That's its name. And we know that diverges. For example, we could use the p-series test. It's a p-series, and the p is not strictly greater than 1, therefore it diverges. Okay, well, let's show, though, that we cannot use the ratio test. If we tried to use the ratio test, what will we get? Well, we get the limit as n goes to infinity of 1 over n, and on the top we get 1 over n plus 1. You just rewrite the sequence on the bottom, and then you add 1 to the variable on the top. So what am I dealing with? Everything's positive. I've got n divided by n plus 1, and it's really easy to see that that gets you a 1. And the fancy word that we'd like to use here is that it's inconclusive. The ratio test is useless for this particular series because it gets us the number 1. Any number less than 1, great, it converges. Any number bigger than 1, great, it diverges. But a lot of series will end up getting you just the plain old number 1, and that means it's inconclusive. Okay, let's also try this other one. Here's a p-series where the p-value is 2, and so it converges by p-series. Here are its terms, and it turns out this is a hard problem. It's hard to show, but it does end up being pi squared over 6. That's outside of the scope of this video. But we do know it converges by p-series because the 2 is bigger than the 1. Okay? And this is another thing that we have to keep straight, is that p-series convergence happens when the power is bigger. But in the ratio test, it converges when it's smaller. So we have to keep that straight. So now let's show that with the ratio test, we don't learn anything about this series. If we tried to use the ratio test, what will we get? We'd get 1 over n squared plus 1 squared, 1 over n squared on the bottom. It's all positive. We get rid of these absolute values. So I end up with the limit as n goes to infinity of n squared over n squared plus 2n plus 1. And again, you could use L'Hopital's rule, you could factor out an n squared. You end up getting 1 for that limit because the biggest terms on the top and bottom are both n squared, so we get 1 over 1 for that limit. However you like to think about that from your Calculus 1 days, that is a 1, and that means that the ratio test, it cannot work, it is inconclusive. So even if you like using the ratio test, and it's pretty useful when it works, there are a lot of problems where it fails to work. We get these inconclusive results, and that doesn't tell us whether, because sometimes it can be inconclusive, but really using something like p-series or knowing that it's a harmonic series, we know the answer is it diverges. But sometimes it's inconclusive and it actually converged the whole time. So we have to be very careful about using the ratio test because it may not work. If we get that 1, we have to scratch it all out. I would scratch all this out and I would try a different test.